We are FTC team number 516, Gears of Fire from Palm Harbor University High School.
Each of our team members train to become experts in particular areas. We strive to become masters in programming, building, designing, and communications.
As a team, we meet about 2 times every week to work on our robot.
We balance our team by cross-training and becoming familiar with other fields. This allows us to evenly divide the tasks among the team members.
We utilize email, instant messaging systems, online document editors, and a variety of other tools in order to communicate when we cannot meet in person.
Spreading the message of FIRST is very important to our team. In order to do so, we organize events at places such as Raytheon, MakerCon, and the Museum of Science and Industry, where we expose the public to FIRST Robotics and our club. Additionally, we know how stressful it can be for teams to have a major malfunction at a competition. Therefore, we prioritize helping other teams resolve their hardware and software issues to the best of our abilities.
We use a digital budget to manage our spending.
Every year, we buy new parts and pay registration fees.
These expenditures are balanced by donations and grants from our sponsors.
We would like to thank Raytheon, Rockwell Collins, Advanced Systems, the Outback Steakhouse Palm Harbor location, and TBTA for making the creation of Marcus possible.
This is Marcus, our robot!
In years past, we've used standard Tetrix wheels in our design. We noticed, however, that our mobility and thus ability to score has been limited by our tank drive system.
This year's game is far more complex than previous years. There are so many different ways of scoring, yet so little time. After several days of contemplation and prototypes, we decided on a holonomic drivetrain. We replaced our standard Tetrix wheels with Mechanim wheels, which allow us to move in all directions regardless of orientation. We immediately noticed a flaw. Our robot had difficulty getting up the ramp due to a lack of traction. Our solution was to put a 15-pound steel plate on the underside of our robot to weigh it down and thus increase traction. Additionally, this made our lift far more stable and reduced the chance of toppling over. However, as other mechanisms of our robot were developed, space became a major issue. Our solution was to create custom ballasts that fit inside our structural elements.
The elements vital to scoring are on opposing sides of the robot. This led to a problem. We had to drive in reverse half of the time.
To resolve this issue, we added a button on the remote to toggle which side was the front. Since there was no way to show which side was active, this caused some confusion. We solved this issue by creating an arrow that points to the current front.
Marcus is equipped with a multifunctional scoop that is designed to filter out the small balls, drop the big balls into the cargo bay, and prevent them from escaping. The design of Marcus's scoop mimics a bulldozer blade. The idea of scoop filtration began when we decided to aim solely for the big balls. We brainstormed, sketched several designs, both in Autodesk Inventor and on paper, and created many prototypes. After several hours of intense thinking and building, we finally created a scoop based on our best design that was lightweight and sturdy. A threaded rod is included for additional support. Zip ties also proved useful to the design as they were lighter than metal and sufficiently strong.
Our lift system comprises of a Lexion cargo bay and a 3-stage linear lift. Also, there is a gate on the cargo bay which controls the containment of the balls. For scoring, balls are loaded into the tray. After the balls are loaded, the lift expands to the appropriate height. Then, the gate releases the balls into the appropriate goal.
As of the present, we have several autonomous modes that allow for versatility in setup. Each of our modes utilizes sensors as well as encoders for precise movement that allows for maximum scoring.